Welcome to this video. In this video, we are going to discuss about band reject filters and all pass filters. Band reject filters are also known as band stop or band elimination filters because in this type of filters, frequencies are attenuated in the stop band while they are passed outside this band, which is shown in the right figure or in the frequency response curve. From the frequency response curve, we can see that frequencies are attenuated within the stop band while they are allowed to pass within the pass bands. Similar to band pass filters, band reject filters can also be classified as wide band reject filters and narrow band reject filters. The narrow band reject filter is commonly called notch filter because of its higher Q value, that is Q greater than 10. Bandwidth of the narrow band reject filter is much smaller than that of wide band reject filters. Here, the circuit diagram of a wide band reject filter is shown in the left side of the screen. It is constructed with a wide band reject. It is constructed with a low pass filter, a high pass filter, and a summing amplifier. The important thing here we have to consider is that in order to realize a wide band reject filter, the low cutoff frequency FL of the high pass filter must be larger than the high cutoff frequency FH of the low pass filter. In the wide band pass filter, we have taken FH greater than FL, but in this case, we have to take FH less than FL in order to assure uh, frequencies are eliminated within the frequency range FL minus FH. In addition, another important thing we have to consider is that the gain of the passband gain of both high pass and low pass sections must be equal. And its frequency response is shown in the right side figure. From the figure, we can see that uh, this figure we can see that this is a low pass filter, and this is a high pass. Here we have the high pass filter. This is a high pass filter section, and its lower cutoff frequency is higher than the upper cutoff frequency of this high low pass filter section. These are about wide band reject filters. Next, we are going to discuss about narrow band reject filters. The narrow band reject filter is often called the notch filter, and it is commonly used for the rejection of single frequency uh, such as 60 Hz power line frequency hub. Most commonly used narrow band reject filter is twin T network, and it is shown in this figure. This is the twin T network. It is shown here. It is a passive filter, and it consists of two T-shaped networks. One T network is made up of two resistors and one capacitor, and the other T network is made with two capacitors and one resistor. It is a twin T network. It is constructed with two T networks. The first T network consists of two resistors and one capacitor connected in the shape of English letter T. The other T network consists of two capacitors and one resistor connected in the shape of a T. These two are connected together, and it is used in the band reject filters to eliminate specified frequencies. The notch out frequency is the frequency at which the maximum attenuation occurs. It is given by Fn equal to 1 by 2 pi RC. The circuit symbol of the notch filter or narrow band reject filter is shown here. It is the circuit symbol. Here we can see the twin T network. The first network consists of resistors R and R, capacitor 2C. The second network consists of two capacitors C and resistor R by 2. And its frequency response is shown here. This center frequency is called notch out frequency, and it is given as Fn equal to 1 by 2 pi RC. In this particular network is chosen because the passive twin network, the twin network is passive because it consists of only passive elements like resistors and capacitors. So its figure of merit is low. In order to increase this low figure of merit when it is used with an op-amp in the band reject filters, commonly we use a voltage follower. This is the voltage follower section. We used a voltage follower with a 20 network. The most important application of notch filters is in communications and biomedical instrumentations for eliminating undesired frequencies. In order to design an active notch filter for a specific notch out frequency Fn, we can choose capacitor value. We can choose the capacitor value C less than or equal to 1 microfarad and then calculate the required value of resistor R. Then we have to find resistor R using this expression Fn equal to 1 by 2 pi RC. R equal to, in this expression, R equal to 1 by 2 pi Fn into C. By fixing the notch out frequency and taking capacitance value C less than or equal to 1 microfarad, we can find the resistance value, and by designing such a circuit, we can notch out the particular frequency. The next one is all-pass filter. As the name suggests, all-pass filter passes all frequency components of the input signal without any attenuation. But it provides a predictable phase shift for different frequencies of the input signal. That is, all-pass filter, as the name implies, they can transmit any frequency input signal without attenuation, but it will provide a phase shift for the output frequencies. When signals are transmitted over transmission lines, such as telephone wires, they undergo change in phase. So, in order to compensate such phase changes, all pass filters are required in order to compensate that phase change. When signals are transmitted through transmission lines such as telephone wires, they will undergo some phase changes. In order to compensate that phase change, we need to use all pass filters. The all-pass filters are also known as delay equalizers or phase correctors. The circuit diagram of an all-pass filter is shown in the figure. In this circuit, we have chosen RF equal to R1. The output voltage V of the filter can be obtained by using the superposition theorem, and it is given by VO equal to minus Vin. It is in the non-inverting and inverting differential amplifier structure, minus Vin plus minus JXC divided by R minus JXC, because a capacitor is here, into Vin into 2. Here we know that minus J minus j equal to 1 by j and xc equal to 1 by 2 pi fc. So substituting, we obtain Vo equal to Vin into minus 1 plus 2 by j 2 pi frc plus 1. On simplifying, we obtain Vo by Vin equal to 1 minus j 2 pi frc divided by 1 plus j 2 pi frc, and its phase difference, phase shift. And its phase shift is given by phi equal to minus 2 tan inverse 2 pi frc divided by 1. Where phi is in degrees, f is in hertz, and r in ohms, and c in farads. The above equation phi equal to minus 2 tan inverse 2 pi frc is used to find the phase angle phi if f, r and c are known. The corresponding input and output voltages are plotted against a phase angle, and here it is the input signal and it is the output signal. Since it is there is no change in amplitude after passing through the filter, but its phase is changed by passing through the filter.